Today, we're going to pull back the curtain on something that powers our entire modern world. It's an invisible set of rules, a kind of secret language, and it's called network analysis. It's the reason pretty much every electronic device you own actually works.
I mean, just stop and think about it for a second. Your phone, the Wi-Fi that's probably delivering this to you right now, the massive power grid keeping the lights on, it's all just staggeringly complex. So how do billions of tiny parts all work together in perfect sync in an instant?
Well, it might feel like magic, but it's not. It's something even more brilliant. The answer is a powerful engineering toolkit called network analysis. This is the set of ideas that lets us understand, predict, and, this is the important part, design all the electrical systems that basically define our lives.
So, to get a handle on this toolkit, we first need to meet the team. You see, every single electrical circuit, from the one in your toaster to the one in a supercomputer, is built from just a few key components. Let's call them the circuit players.
First up to bat, we've got the resistor. Its job is pretty simple. It manages the flow of electricity. You can think of it like friction for electrical current. It pushes back, it resists the flow. And in doing that, it uses up some of the electrical energy, usually by turning it into a little bit of heat. It's absolutely crucial for keeping voltage and current levels exactly where they need to be.
All right, next we have the capacitor. Now, unlike the resistor, the capacitor doesn't waste energy. It saves it. It's like a tiny little battery that can charge up and discharge almost instantly, storing energy in an electric field. This is the component behind everything from the flash on your camera to the filters in your sound system.
And rounding out our starting lineup is the inductor. It also stores energy, but it does it in a magnetic field. Now, what makes the inductor special is its personality. It hates change. It actively fights against any sudden change in the current flowing through it, and that property is fundamental for things like power supplies and tuning into a radio station.
So let's just do a quick recap here. The resistor is the energy consumer. It controls the flow. The capacitor and the inductor, they're the energy savers, storing it in electric and magnetic fields. These three are what we call the fundamental passive players on the team. But here's the thing. These passive players, the ones consuming or storing energy, they can't do anything on their own. They need some juice. That's where active elements come in. These are the parts that provide the energy. Think of a battery or a power plant or just the outlet in your wall. They're the ones that get the game started for everybody else.
Okay, so we've met the players, but how do they actually interact with each other? What are the rules of the game that they all have to follow, no exceptions? You know, it turns out that every circuit in the entire universe, no matter how big or small, has to obey two absolutely unbreakable laws. They are the fundamental rules of the road for electricity, and they're called Kirchhoff's laws, named for the physicist who figured them out way back in the 19th century.
So, the first law is all about current. It's called Kirchhoff's current law, or KCL for short. And honestly, it's just a statement of conservation. It says that at any junction, any spot where a bunch of wires meet, the total amount of current flowing in has to equal the total amount flowing out. It's that simple. Electricity can't just appear out of nowhere or vanish into thin air.
The second law is all about voltage, and this one's about the conservation of energy. Kirchhoff's voltage law, or KVL, says that if you trace any closed path, any loop, in a circuit, the voltage you gain from things like batteries has to be perfectly balanced by the voltage you lose across components like resistors. By the time you get back to where you started, it all has to add up to zero. Kind of like hiking up a mountain and then back down to your starting point. Your net change in elevation is zero.
So now we've got our players, and we've got the fundamental rules of the game. And with just those, you could, in theory, analyze any circuit you want. But there's a pretty big problem.
What happens when you're not looking at a simple diagram in a textbook, but you're looking at a microchip with literally billions of components? Trying to apply those basic laws to every single part one by one? Forget it. It would be an absolutely impossible task. You'd be there forever. This is where the real beauty of network analysis starts to shine. Engineers came up with this amazing set of clever shortcuts called network theorems. These are these powerful techniques, like Thevenin's theorem or superposition, that let you take a huge, complicated mess of a circuit and replace it with something incredibly simple. It makes these giant problems, well, manageable. And this really shows you the difference. On one side, you've got the brute force method. You're just slogging through, applying the basic laws over and over again. It's slow, and you're bound to make a mistake. But on the other side, use a theorem to boil down a huge part of the circuit into a simple, elegant equivalent. It's about working smarter, not harder, and focusing only on the part you actually care about. So we have our players, the rules, and some seriously useful shortcuts. But for the most dynamic, most challenging problems, engineers need to break out one more level of their toolkit, the real power tools of analysis.
I mean, how do you even begin to analyze circuits where the signals aren't just a steady, constant flow? What about audio signals, or radio waves, or your Wi-Fi? These signals are constantly changing, and that makes the behavior of our players, especially the capacitor and inductor, way more complicated. The math can get really messy.
To tackle this, engineers use something that sounds super intimidating but is actually a beautiful idea: mathematical transforms. Things like the Fourier and Laplace transforms are basically like universal translators. They take a really difficult problem written in the language of time and translate it into a different language, the language of frequency, where the math suddenly becomes way easier.
So here's how this magic trick works. 1. You start with your difficult problem in what's called the time domain. 2. You apply the transform, which is like a secret code that zaps your problem into the frequency domain. 3. Now, this is the best part. That problem that involved all sorts of nasty calculus, it's often just simple algebra now, so you solve the easy problem. 4. You apply an inverse transform to translate your simple answer back into the real world. The whole strategy is just a brilliant way to dodge the hard math.
So let's recap. We have the players, we have the rules, we have shortcuts, and we have these incredible power tools. We've just put together the complete toolkit for network analysis. But, so what? What does all this actually let us do?
And this is the most important part of all. This whole toolkit isn't just for looking at circuits that are already built. It gives engineers the power to do something much cooler: synthesis. That means designing and building brand new technologies from scratch. Analysis is about taking things apart to see how they work. Synthesis is about creating things that have never existed before.
And that act of creation is literally all around you. These principles are why the filters in your speakers can separate the bass from the treble. They're what allow us to design stable power grids that stretch across entire continents without collapsing. High-speed communications like fiber optics and 5G totally depended on this stuff. And of course, the ridiculously complex microchips inside every single device you own are maybe the greatest example of what this toolkit can build.
So the next time you pick up your phone or turn on a light or connect to Wi-Fi, just remember that under the surface, there's this silent, elegant language at work. It's a system of players and rules and incredibly clever tools, all working together. It's the invisible grammar that's constantly writing the story of our modern world.